Hey guys, welcome to your second lesson on the work energy theorem. In this lesson, we're going to focus on forces that occur on an object, but what did we work with before? We worked with one force acting on an object. Now we want to introduce two forces and see if we can cope with that example. Remember that the work energy theorem can be extended to include potential energy. So when we have conservative forces, potential energy can be developed for them. What that means is that we can include potential energy within our calculation. That potential energy will be added to the right-hand side of the equation. So let's look at the following example and see how we do.
So let's first look at the definitions. So the definition of a conservative force, which is what I have, the definition says a force is said to be conservative if the work done by or against the force is dependent only on the initial and the final position of the body and not on the path that the body will follow. So the work done by the conservative force in a closed path is zero. And some examples of this is gravitational force. So do you remember we said that force of gravity acts on you, that is keeping you upright from the ground. You get a magnetic force, so where two magnets will put a force of attraction or a force of repulsion. We know that another example is an electrostatic force. So there are many other examples of conservative forces, and you can look them up if you'd like to know more on them. And then we want to look at a non-conservative force. So a force is said to be non-conservative if the work done by or against the force is dependent on the path. So all that matters is that you need to know, is the movement of the body important or not important. The work done by non-consecutive forces in a closed path is not zero. That means that it needs to be calculated. Some examples of those forces are friction, viscous force, induction, and forces in cyclotron or other types of forces. Remember that if you want to know more on the conservative forces, then you can have a look at the examples and try to research them and see how they actually work and how they will affect conservative or non-conservative forces. We then can look at the work energy theorem. So we said that the work energy theorem looks at combining energy and work. So what that work energy theorem states is that the work done on an object equals to the change in the object's kinetic energy and or gravitational potential energy. So that means that the work energy theorem states that the work done on an object by the net force is equal to the change in its kinetic energy. Remember, we want to have a look at the different formulas that we can use. We can look at the work total or the work net. So wherever we see the word total, we want to associate that with the word net. So total, we associate that with the word net. So work net is equal to the change in kinetic energy. The change in kinetic energy will equal to the final minus the initial, and then you calculate them each independently. Or gravitational potential energy, where we look at the formula for potential energy as the gravitational energy, the final minus the initial, and then break it down into its components. We can then see that the change in kinetic energy is equal to the negative change in potential energy. Why do we say negative change? What did we learn about kinetic energy and potential energy? We learned that they are inversely proportional. As kinetic energy increases, potential energy decreases. as potential energy increases, kinetic energy increases, but they increase and decrease within the same magnitude. Why do they increase and decrease by the same magnitude? That is because during the magnitude or the change, we know that there is a conservation of energy, which means that energy cannot be lost or created or destroyed. It is rather transformed from one form to the other. Using what we know, we can look at the following example. It says, the driver of a 1000 kg car is traveling at a speed of 16,7 meters per second. Now in that car, the car applies the brakes when he sees a red light. The car brakes, which provides a frictional force of 8,000 newtons. Determine the stopping distance of the car. So what do we have in this example? We have the mass of the car, which is equal to 1,000 kgs. What else do we have? We have the speed, and speed is also the velocity, which is equal to 16,7 meters per second. And then we have the force of friction, which is equal to 8,000 newtons. We want to know the stopping distance of the car. So the first step is to look at what is given and see if they all are in their SI units, and they are. Then we can look at step 2. Step 2 is to determine how we are going to approach the problem. What are we going to do? We want to apply the work energy theorem. We know that all the car's kinetic energy is lost to friction, and therefore the change in the car's kinetic energy is equal to the work done by the friction. So we can therefore first need to determine the car's kinetic energy at the point of braking. So the first step is to look at the kinetic energy, which is equal to E, or energy of kinetic, which is equal to half m, which is the mass, times velocity squared. Once we have done that, this energy is equal to the work done by the brakes. So we have the force that is applied by the brakes. What can we use? Do you remember that we learned about work, and we learned that work is equal to F delta x cos theta. So let's work with step 2. Let's calculate this. The next step is to determine the kinetic energy. So let's calculate. Half, what is the mass? The mass is 1,000 kgs. What is the velocity? 16,7 squared. So what is my kinetic energy going to equal to? It's equal to 139,445 joules. The next step is to look at work. We are assuming that at the stopping distance, we're going to assume that the change in the distance is 0. So assuming that the stopping distance is 0, since the direction of the applied force and the displacement is in opposite direction, so it's friction works in the opposite direction, we can then say that we want to calculate this. Force is equal to the 8,000 newtons. Delta x, we assuming to be delta x at the initial, and then we get cos of 180 degrees. So what am I left with? When I calculate this, I know that cos of 180 is minus 1. So I'm left with minus 8,000 delta x initial. So we don't know what that delta x is. We then want to take what we have and we want to apply the work energy theorem. So we said the work energy theorem says that work net is equal to the change in the energy kinetic. So what is the kinetic energy change? It is the energy of the kinetic energy final minus the energy of the kinetic initial. What is that change equal to? We can say that we calculated, so this is work net, we calculated work net, and work net was minus 8,000 delta x 0, and that would be equal to, what is the kinetic energy final? There is no kinetic energy once the car has stopped. Remember that kinetic energy is movement. Once the car has stopped, it has zero kinetic energy, minus the kinetic energy at the initial, which is 139,445. Once I have that, I can say that delta x is equal to minus 139,445 all over minus 8,000, and that's going to give me a value of 17,4 meters. So what have I done with this? What have I calculated? I've taken the example that I've had. I've calculated the kinetic energy that was needed. I then calculated the work done. I then used both of those examples to do an equation that will give me the final answer that I needed, which is the stopping distance of the car. I used the work energy theorem to calculate that stopping distance by using the values that I created for kinetic energy and work. Once I'm done, I will state my final answer, which is that the car stops in 17,4 meters.
Well done, guys. We got through that example. I hope that you were following, because it was a very long example that we had to go through. Remember that with work energy theorem, there are various different components that we need to take into consideration. So with it, log on to the iWiz app and our website for more information. The website will give you access to worksheets that will help you improve this section. Good luck with it.
We need to learn to live with the COVID virus, the new normal, at least for the next few months. And we have just what you need to make sure you never miss a single school lesson. And it's absolutely free, mahala! High quality, powerful, animated lessons for all your subjects. So don't spend a cent until you have tried iWiz. It's everything you need. All video lessons, textbooks, workbooks, exam prep. We want you to ace 2021.